Let's spending the next 15 minutes in a rocket. We are going to have a very fast-paced discussion because there are lots of materials. So since about 3 years ago, LM was launched, and I work with Professor Monica Lam, who happened to be working on virtual assistant for several years. But we always kind of hitting the bottleneck. The natural language understanding, natural language processing, just like Andrew Ng, another professor at Stanford saying, well, when NLU is effective, it's like 95% accuracy, not many people will use it because you have this virtual assistant, you talk to the virtual assistant 95% of the time it's okay, but 5% of the time misunderstood you and lost the context, you get quite upset. So yeah, that's a popular situation. We were in the dark ages for some time, but once LM at the time was like 2.5 and 3.0 launched, the landscape suddenly changed. And when 4.0 came out, for sure there are some kind of importance and the killer application came out. But still, definitely not sufficient. As Yang Lukan said, LM suck. He used the word suck. LM doom. Okay? And he enumerates certain constraints on the current LMs. But our position is LM is still a viable foundation for moving toward AGI. We just have to do system 2. System 1, LM, is just a pattern repository, period. There's no semantic, no ability to do reasoning, but has the ability to do correlation association. Therefore, we have to be very careful. We are not going to trash LM, because LM itself has an extremely positive value. When LM was discovered or developed, was for a purpose. If you remember, the first sort of like transformer product was BERT from Google. When they built BERT, there was a reason for building that. They didn't build it for just having these large models. So if you know that reason, you cannot really trash LMs. Okay, let's start it from the discussion. I'm going to talk about these 6 topics or 8, but I'm going to skip some of them. And this book is in the public domain. If you take a picture, the QR code, you can access the book for free, download for free. If your institution signed up to ACM Books, or you personally is an ACM member, okay? And please just be generous to distribute other students, and it's a good reference to keep. So, as Oussama this morning gave an outstanding talk, we probably kind of accepted robotics motion largely solved. In certain situations, challenging situation, multi-situation, whatever, of course, there are some corner cases, but it's kind of much better compared with haptics. I mean, we talk about haptics, there are still kind of quite some challenges to be overcome. But we would say very quickly, bottom line, is both vision and motion are probably largely kind of solved. There are still some corner cases, but haptics is a key to let us to kind of reach home. So if you look at potential killer apps, as we discussed in the panel session, there are certain things can already been done, like probably manufacturing, doing assembly. You know, in Amazon, they have probably more than 50,000 robots doing repetitive work. So yes, they are productive, but may not be good enough. So we look at robots, they need to have vision. If you have one robot, the vision is probably pretty narrowed, right? So if you don't tell the robot where to look into, so where to pay attention to, the robot is just very passive. So you have to do certain planning. So when you have multiple robots, now you have a much kind of wider perspective, wider scene spatially, and you can knit the field together. This is all well-known technologies and has been developed in the last maybe over 30 years by computer vision people, by robotic development, and so on and so forth. So today, if you say I have a robot patrol the street, I have no problem to do object detection, even object recognition, and sometimes countries using this camera, like when we check into the airport nowadays, they just take a picture, right? This is just amazing. But then you look at the application, you say, well, the Boston Dynamics is very impressive and do flipping. So what else? What else we can take advantage of this robotics? And there are billions of dollars, VC monies out there. They dying to kind of invest in kind of killer apps so everybody can be benefited. But still, we are not there. I mean, there are quite a few things we are not there. But today I'm probably quite trying to focus on the software side. Okay. So this slide shows, okay, starting from survey the field, identify patterns, computer vision, then grounding semantics. And after ImageNet, which I happen to be the sponsor of the project, and the problem has been largely solved. And of course, I mean, it's not perfect. But then we say, well, can we not just only have one LLMs? So suppose we have multiple LLMs, and lots of people are going into that direction, have good justifications, and it doesn't work that effectively for some reasons I will disclose to you. But the idea was not bad, because if you're thinking about human intelligence, human, maybe evolution or human advancements, and Socrates used to say, human intelligence was developed by thesis versus antithesis. Then you have synthesis disagreement between the two guys, two people or two women, and eventually after the synthesis, you don't have consensus perhaps sometimes. You don't just do majority voting. You may have new generation, right? Generate the new ideas, whatever. And that's intelligence. So when you have multiple agents coming together, if you orchestrate this entire multi-agent system correctly, there could be something interesting. So we really want to push from body to mind. So just very quick example, very simple example. Suppose we want to, this is a project initially wanted to work with the University of Maryland. So suppose we want to pursue a thief on campus. We have robots doing patrolling. And this is not very simple saying every robot has its own view without coordinating with other robots. Not only you have to coordinate with other robots because they can see other different places, but also you have to do projection. Projection means, oh, where this thief is running toward, the direction. So you are not going to just run to the thief's current location or suspect's current location. You want to project, right? Maybe in 5 minutes, he or she will be somewhere else. So, but currently, this is the situation, right? You see, the thieves is laughing at the robots just fail. I mean, they cannot coordinate really well. And likewise, in hospitals, we really like to have robots to come in to help all the logistics. Like FFAD has worked with Stanford Hospital, having cameras installed in many places and monitoring the nurses, whether the nurses come into the room, whether the nurses has washed her hands, whatever his hands. And those are kind of really, really minor components. Still, it's already kind of improvement, but there's much more things can be done. And nursing home, we talk about it, right? And we have a speaker or our panel talk about, we have this aging problem. We have the next generation population get really smaller and smaller. All the country virtually is facing the similar problems. So we need to have effective help. And so if you look at even these kind of problems, 24 hours elderly care. And the robot, each robot may have specialties, right? Robot has diversity kind of skill, currently is kind of hard. So I saw a robotic maybe demo in Oussama's lab, and the robot can change in hands, different hands or doing different things, and that's good. And maybe more practical is maybe a different robot is kind of just a robot doing cooking, another robot will be doing sweeping the floor, and using one robot to do all the house chores. It's possible, but it can be a little bit challenging. And anyway, what goes wrong, if something goes wrong in this entire process, right? You do a planning, I have an example shortly. You do a planning, but the planning can go wrong. You say, okay, you go to the room to visit this patient and measure this patient's vital sign, and then you give the medicine to the patient. And if you say, I walk to the room and the hallway was blocked, what would you do? If this is not well planned, if the robot cannot react, then this is challenging. If you go there, the patient is not in the room, what would you do? What would you react? So all those things you cannot say, oh, okay, call down, there's nothing I can do. You have to kind of foreseeing what if, all those kind of situations. And not mentioning this is on the back of everybody's mind, right? You know why people, why nations investing so much into AI, because they are really worrying about if they are lagging in this domain, they will be wiped out. Right? So everybody understands. And then if you want to do such, and it's much, much more complex. So in the drone scenarios, and you have different drones looking at different situations, and every drone, maybe one drone flying to zone 1, and he says, well, this is very safe, everybody can fly in, and oh, accidentally it was shut down. And how do you communicate the situation to other drones so they can changing their navigation or the path? So without saying even further, I think you understand. When I presented all these challenging scenarios to some Taiwanese students last December, I was mocked by saying, Edward, we have done everything. Because have you seen this celebration? See all the drones flying together? Are you kidding me? This is perfect. AI was perfect. Okay. So, but like Oussama and us, a lot of people in Stanford, we are still foolishly develop the advanced methodologies. And Professor Oussama saying, well, operation space formulation came up with this big idea many years ago. Still, we still need to be able to making sure the space is well formulated, and there are various control physically and also even in reasoning. And recently we applied control theory to reason, and hopefully the reason can be more rigorous and can be more robust, and also human-friendly robotics and so on and so forth. So the rest of the talk will be funded by the volume 1 of my book, just shown you. The second book is on the way. Maybe by March I will be able to finish. Now it's under revision. It's already finished 7 chapters. And the first book is pretty much about systems. The second book is purely devoted to reasoning. And I was surprised. Not many kind of research has done in the field. The major reason is because short of benchmarks. So I will talk about benchmarks in a few minutes. So in the first book, we had many pillars, but we are going to just focus some relevant ones to our current focus. Okay. So if you want to have multiple agents coordinate together, every agent managing each robot, or multiple agents may coordinate one robot. And there are many reasons you probably want to do that. And what you probably want to do, instead of looking at the name much carefully, but we need to start to say, okay, this is a set of robots, and they have certain dependencies between their tasks. And there are temporal spatial dependencies. And when they start to do certain things, and you probably need to log their activities. And currently, LLMs just do one thing at a time, and once it has done its own thing, maybe forget about the memory. And even in the context buffer is still sitting there, LLM is notoriously have the problem of forgetfulness. The reason is because if you scan the buffer of the context, this attention model is stochastic. So if you have a program, say S1 to S10, each assign a variable, and everyone is being attending 100%. So later in the program, you say, what is S5, S7? You don't have a problem. But in the context, when the context grows really large, there are 2 problems. One is a variable assigned to 3 got forgotten because that particular token was not high in probability. And the second problem is if the value was modified, S1 equal to 7, then become 10, become 7 again, and you don't have the history data, so you lost track. So when I work with LLM, I often have this kind of problem. I say, okay, start writing this piece of code, and it had a bug. So I say, okay, fix that problem, and you should be doing this and that, and maybe I ingest certain code, and you modify it, and then the new code has a new piece of bug. Then I say, okay, now there's a new piece of bug, fix it, whatever. Then the old bug shows up. And I say, eventually I was so frustrated. I have to do my dues. All my bad manners showed up in front of LLMs. My family was not in the room, so I can start to say something really bad. And the LLM will say, oh, I understand your frustration. I apologize. But again, repeats the error. So that's one of the problems. It doesn't really can save its constraints persistently. So Yang Lukan was right. Yang doesn't have persistent memory. But that's not a big problem, right? So if you look at the picture here, oh, Saga happened to be my advisor's master invention. And Saga, the idea is you want to log your history, but you don't want to log everything. Some people out there saying, oh, I'm going to just dump all my contacts into a vector database, and then I will just retrieving them back. But if you don't have history, and you don't have schema, and how are you going to go do retrieval? Retrieval is going to be very time consuming, and the resolution is not very good. And number two is your indexing structure kept in the memory also will suffer from context loss. So I have no idea what people are aiming for. But the key thing you have to say is, if LLM is smart enough to identify in your whole workflow, so again, alarms. What alarms would do is to say, if you give me a piece of work need to be accomplished, and it mainly would do the right-hand side thing. I am going to formulate a workflow, right? And on the workflow, I have multiple agents or multiple steps. If I only have one agent, I have multiple steps. If I could have multiple agents, every agent has multiple steps, and multiple agents interact with each other. So you have this big cyclic graph, potentially cyclic graph. And in sequential kind of planning, this problem is largely solved. And in the operation research or in computer science, travel salesman problem has been largely solved. It's an NP-hard problem, but you can approximate this problem using this dynamic programming or simulating annealing. So that's okay. It's approximate, but it's good enough, right? So you said, Edward, then why bother to do it? In fact, if you give LLM a sophisticated planning problem to solve, the smart LLM wouldn't solve it for you. Because the smart LLM pretend to be smart. It's going to treat it as a combinatory problem, to enumerate all the possibilities and give you the best one. But you know there are virtually huge number of alternatives, right? So-called combinatory problem. And so what good LLM actually did was, I'm going to call subroutines. I'm going to call operation research subroutines to solve the problem for you. That's exactly the right thing to do. But if you have the second problem, called reactive, you have surprises, you encounter some problems, like the one example I gave you, a robot get into the room, and the patient was not in the room, maybe in the bathroom, maybe just went out to give a walk. So then what do? You have to react to the situation. And sometimes you want to preemptive, means I haven't faced the disruptions yet, but what if I drive to the airport, something happened, traffic jam, whatever, then what should I do, right? So those things need to be done, but those things can be done by LLM, and doesn't need to rely on the traditional OR methods. In fact, if you want to do replanning, you want to rely on traditional OR method, you are shooting yourself on the foot. Assuming you are in TSMC, and finally you have this entire manufacturing floor mapped out. You have machines, you have operations, you have wafers coming in. And there's one machine misfunction. And you say, oh, now I'm going to run the OR again. I do replanning for my old job shop. You must be kidding. You have so many work in progress sitting here and there, wafer get half baked or half kind of etched. You cannot do that. You can only do local repairment, and when you do local repairment, you want to be very careful the cascading effects minimized. So that's exactly where LLM should come in. And either LLM, this is a minor kind of fixes. Even it's a combinatory problem, but the number of elements get involved is minimum. LLM can deal with. But you deal with it carefully, because you don't want to have your agent having a large context. But you don't want to deal with the problem, but you keep on losing your memory. So in short, what ALAS is doing, is adaptive LLM agent system, is going to just decompose your problem into a massive workflow and putting constraints in separate constraint management LLMs. Those LLMs will load constraints into hard disk or flash memory, so make sure refreshing constantly, and you have global constraint management to oversee everything. And then you have code get generated. So this is interesting. We are not going to write code. Traditionally, if you do a database system, transaction systems, the engineer will be coding, because I was a coder for 9 years, very, very sad. And you have to code a lot of things. Then you have to imagine all the exceptions. You have to code them in. But when LLM is present, LLM can actually see some novel situations. It could deal with you. But in the past, if some novel exception comes out, the system has no way to recover from. So this is, I think, the beauty of it. The interesting part, some reviewer in the conference will say, well, the code may be buggy, but it's not too hard. Once you have this LLM generate code, you can have white box testing, black box testing, regression testing, whatever to test your code, and then you can do a lot of validations. And all the code has bugs, right? So you don't reject a paper because the code generated by LLM could be buggy. But I think this seems like reasonable, and you have runtime management. So started with a meta planner. A meta planner gives you a workflow, but the workflow is just a plan with no programs. Then you get the meta planner. You instantiate your meta planner into a real workflow, and every node you assign an agent. You know exactly the input-output operation of each agent. You start to write code, and you have constraint management, everything together, and then your second step, you have realized workflow. Then you put them into the runtime. And there are some implementation choices. If you want your runtime to be scalable, you have to use Amazon services. Otherwise, you can use other services. So we have been doing coding myself for the last 2-3 years. And it's been really, really fun. So give you this very short example. Suppose this nurse go into a bedroom and try to do this process we just mentioned. So this is one thing need to be planned, right? So this is a sequential planning, static planning, optimized, fine. And then you say, wow, there are many other kind of scenario, much more complex. You can manufacturing, you can have this container shipment, cargo allocation. This is one of the hardest problems probably you don't know. And Singapore is doing really, really well. Because when you put things into the container, you want to make sure when you try to, where you put placement is really challenging. Oh, okay, so then job shop. This is a big, big problem. And I talked to TSMC already for a year. So you have a number of machines. Every machine can deal with perhaps a couple of different operations. And then you have jobs come in. Every job needs to go to different machines to be operated. So thinking about, you have a wafer comes in. This wafer, on that wafer, you have 4 kinds of dies you need to manufacture. Wafer is not huge, but you know the dies are 3 tiny. One wafer could have 10,000 chips. And some chips from Apple's order, some from NVIDIA. So you have to really be very careful, and you have to go to different machines. And those scheduling in the middle can be also very dynamic. For instance, the memory chip, right? So you say, oh, memory chip. I have 3 grades of memory chip. Grade 1, grade 2, grade 3. And so I have enough order. But I know I need to do quality control. If grade 1 fails to be grade 2, it's not a disaster. I can ship to this company, right, with a lower price. So that's kind of interesting. Financial management also need to be in place. So all those, put it in. But in this case, right, you go to, the nurse goes to the room, the patient is not there. What would you do? So waiting there for 20 minutes, or you have to go back to the desk, and so on and so forth. Those are sort of exceptions. In the manufacturing floor, everything is dandy, very good, but disruption happens, so that machine gets shut down. Oh, you have this cascading problems. How do you do this local kind of rescheduling without causing too much problems? And there are interesting, robust, greedy methods you can do, and you kind of have limitation of how many cascadings I'm able to tolerate. If I cannot tolerate, then fine. We just have a suboptimal mark time. So pushing the schedule out, right? The goal is to minimize the mark time. So therefore, with the same amount of time, I can have higher productivity. But if I want to minimize the disruption, so here you can have a penalty function saying, oh, if cascading is too much, minus 2 points. If you want me to cascade and also moving the work in progress somewhere to somewhere else, that would take more time, would waste my resources, penalty. So that will be able to constrain this mitigation situation. So that's great. But let's look at this. Long horizon static planning. a loss, fine, no problem. Reactive planning, OR doesn't work. So LLM work to a certain degree, but we need to mitigate by persistent memory. And I think this is wrong. This should be preemptive. So I think didn't have spelling accuracy. Preemptive, LLM cannot do it, and I will talk about preemptive slightly later. The LLM cannot deal with what if really well. Okay. So I mentioned this problem is solved largely, but in real world, this is a kind of Uber scheduling. And now we have this self-driving vehicle in San Francisco. Weimar is probably start to service the travel to airport. So you can say in different locations, people calling Weimar to come here to pick you up, and a car can be shared by multiple people, right? So this seems to be very straightforward. Given the problem, we convert to this meta planner, but you have some people already waiting. But meta planner get converted to be a real workflow. And a real workflow, we have our scheduler. We start to do real scheduling. And real scheduling actually is done by 2 LLMs. And based on 2 LLM running our last algorithm. And one is better than the other. So we say, okay, good. We pick the better one. But when there's a disruption, so here the disruption we kind of forced was saying, oh, there's an accident on the highway. The accident is between maybe D to the Boston airport, or we don't know the location. So now if you don't have temporal spatial information of all vehicles, what can you do? See, if you know there's an accident somewhere, there are 3 scenarios for each car. I am in front of or before the accident spot. So therefore, I will be slowed down. So you have to multiply your expected arrival time by a factor. Second thing is, I already passed, or I'm at a different direction, so I won't be affected. The third one in low probability is, I'm there. I get into accident. Right? So, but you need to have spatial temporal logging in this situation. The history has to be logged. So when that happens, and your master schedule can quickly look at the GPS location of your car, not moving where you are. So rescheduling will be possible, saying turn around, or you ask another backup vehicle to do whatever. Right? Okay, this is just a simple example to show disruption is hard to handle. Once we can handle that with persistent memory, and our performance in different scenario works much better. For different scenario means we actually publish a benchmark paper. You know, in these days, not just trying to publish a paper to do kind of beauty contest for yourself. A lot of time you need to do community service, especially when you're addressing novel problems. They are lacking benchmarks. So we spend a lot of time to build a large planning benchmark, and KDD accepted, and these are like kind of our empirical study results. And recently we just asking a student of, like say, almost 100 in the beginning, building this causality benchmark we will talk about shortly, okay? So we always encounter value surprises in real world. And even just 3 to 5%, it can cause your business to be really suffering. And we need to have transaction properties to be able to do compensation or rollback. And if you are not familiar with compensation or rollback, and for rollback in digital world, suppose you deposit your money and then the ATM machine failed. Either you cannot deposit, you get your money back, or the money is in the bank, right? But in the real world scenario, undo redo doesn't work. Like medical operation, when you suffer from certain kind of diseases, your liver will be operated. That's not called undo redo. That's called compensation. Or you spill the milk in the kitchen and you cannot unspill the milk. You have to wipe out the floor and you be chastised by your wife saying, "What did you do so?" and suffering for some time. So that's called compensation. Okay, compensation has to be performed by your robot sometimes. So not going to get even further because I think you get the point. Saga LLM, its mission is to do logging, and this logging is intelligent logging, not dumping everything. by logging the important spatial temporal information. So when there is exception of value, we have a chance to come back. So this is very simple example. So suppose you open a valve, and it doesn't work. What do you mean unopen, right? You have to get it work, so your compensation has to be, I'll close it. I need to drain it. So therefore, then I open it again. So get the point, okay? And they work hand-in-hand together. So this is kind of two-phase workflow. Good. And another problem in robotic precise is this interesting challenge where persistent memory probably need to come into play. Because the physical robot itself is like a spinal cord. The response time is about 500 hertz, maybe even quicker. But when you talk about cortex, you want to communicate with LLMs or intelligent being or system 2, and that would take more time. So there is a lag between the two. So if you say the current state logged in my Saga LLM is saying the door is open, but when the robot just walking through the door is closed, so you have to update right there because the robot sees something like spinal cord faster than your real world, sort of like the cortex registration. So that gap, I haven't do simulation yet, but this is a problem. It's slightly different from other real world problems. So there's a gap delay over there. But in any rate, just repeat, the performance is okay. So finally, the final time I'm going to devote on to reasoning, okay? So we know reasoning per ladder has 3 levels. Level 1, association. And if you see A, you see B at the same time. And association has been poisoned the society for years, right? Recommendation basically saying, oh, when other people look at this ads or look at this Facebook page, they will click on that. So therefore, when you see this, I'm going to show you that. So you have higher probability will click on that. And then if I profile you, that will be even better. When your friends see that page will click on that ads, you are similar to your friend's behavior, then I'm going to do the same thing to you. And that's called association, that's not causality. But when you get to the level 2, this intervention is causality, cause, what causes what. And the third level is much more challenging, what if. Okay, so let's quickly look at the level 1. Level 1 always suffer from, I would say, don't say always, but if you are not very lucky, you will suffer from Simpson's trap. Simpson's trap means you consider A associated with B, so you say either A causes B or B causes A. In fact, they are not causing each other. You have another reason causing both. So one classical example conveyed to some audience was, oh, ice cream in the summer or the sales went up, and also people drowning in the ocean also went up. So ice cream sales causes more death in the ocean? No. Hot weather is a confounder. And there are 2 other examples here, and this is a famous lawsuit toward UC Berkeley. Some ladies saying they got discriminated because admission rate for ladies was lower, but once they found the confounder, they said, oh, sorry, because women tend to apply for department has lower admission rate. So once you get the confounder, you say, oh, okay, there's no discrimination whatsoever. So another one, the premium hospital has more fatal death. And you say, well, I'm not going to send my parents to National Taiwan University to get treatment. That's higher death rate. But the problem is, when you have a fatal disease or in your family, you want to send them to the best hospital. Of course, the hospital will be entertaining people with more severe cases, so therefore they have a higher death rate. The confounder is the percentage of people get sent into different hospitals. Urgent care or the clinic around the corner of the street, you wouldn't send a heart attack patient over there. Of course, they wouldn't have this kind of fatal death. So we are suffering from all this kind of association pretending to be causal by LLMs. And there's no way to escape, absolutely no way to escape. And sometimes we are lucky for 3 reasons. One is, it happens to be an association kind of scenario, but the data was creative with a causal analysis. And maybe the second thing is, you have data in the repository, you can do a kind of check. So consensus may not be truth. And this is what we need to be very careful about, okay? Another thing is also in the reasoning process, this is recently found out. I mean, we knew about hallucination for some years. Hallucination is actually not really someone crazy give you some kind of nightmare or dreams. It's like, I want to give you the next token, but all the next token probability is very, very low because in all your corpora, behind this particular word, I just couldn't find many articles having that word. So I'm going to give you the nearest neighbor, right? This is, when you do search, always you go for the nearest neighbor. But sometimes you don't have nearest neighbor. Your nearest neighbor is actually living very far away. So you say, okay, he's the nearest, but he is in Taichung. Okay, I'm going to grab that data to give it to you. And you look at it, you say, hallucination. No. From mathematical perspective, it's doing its own thing. It's doing the right thing. It's your data problem. Okay, the next problem is sycophancy. Sycophancy is really kind of bizarre. I think more people get kind of this feedback from your LLMs, right? When LLM gave you an answer you don't like it, you say, no, that's wrong. I think you misunderstand my question, you should do this. Or even you say, 4 plus 3, what is the answer? LLM say, 7. I say, no, I'm a professor. It should be 23. I say, LLM say, no, you are wrong. It should be 7. I say, no, think about it again. So you're going to hallucinate a chain of thought, which will give you the desired number. You say, 4 plus 3. So 3, are you implying 3 means 3 dozens? So okay, it's whatever you want. Maybe should be 40, right? 4 plus 3 times 12. This is called sycophancy. It means try to kiss you up, okay? And why LM has this behavior? This is a construct. From the beginning to now, I always just don't like it. This is called reinforcement learning with human feedback, right? Richard Sutter won the Turing Award last time, and he said it very, very clearly. Reinforcement learning works only when you have invariant truth to verify. So if you use reinforcement learning to play AlphaGo, to do protein folding, which exactly have the resulting structure 3D, invariant. So, DeepMind wins all the games because all the games has precise rules. Input is discrete. Input is not stochastic. Your output is either win or lose. You compare with medical disease diagnosis. Your symptoms, maybe sometimes people complain about symptoms, but very fuzzy. Right? I have a high headache. What do you mean you're high and my low? Right? I have bigger tolerance. And you may have, how many diseases can you have? There are 800 diseases out there. So I can give you maybe 3 highest likelihood one. Unlike the Go game, either you win or you lose. And also feedback could be subjective. So in the end, it will be majority voting. And sycophancy, because LLM get used to reinforcement with human feedback, you say, I like to get a thumb up. So that's the problem we are facing right now. And then you look at the statistics, you'll be surprised. The dump LLM, let's say 3.5 is probably primitive, more primitive. 5.1, 5.2 is frontier, right? So you tally their accuracy with a benchmark. This is a very simple math benchmark in the public. And yeah, great. People publish saying, 5.2 is doing great. Accuracy is high. But then you say, I'm going to put a judge. After you answer the question, I'm going to give you feedback. And this is the feedback. Sometimes I would say, no, you are wrong. So you should change. And we give 2 different kinds of feedback. One is very polite feedback. You could be wrong. Would you please reconsider? The other feedback is very strong, saying, you are wrong. You have to fix it. You are so stupid. And we say, well, both kinds of feedback, would the LM change its mind? And it does. The smarter you are, the easier you will get into sycophancy. Right? The stupider you are, the stupider the LM is. Like GPT 3.5 doesn't have chain of thought. So you say, there's nothing I can sequence about. But 5.1, oh yeah, I'm going to imagine. If you really want to have that answer, I can imagine the chain of thought to give it to you. I think 5.2 mitigate the problem to some certain degree. But this is a curve, really interesting. Higher the accuracy, higher the sequencing. Why I need to talk about this? When you have multiple robots start to talk to each other and in the battlefield, and one say, I see an enemy here and there, whatever. The other one says, no, you are wrong, whatever. This could also happen in that communication situation. The communication is not like we said in the past, oh, whoever is in that direction, so just trust me. The communication under this kind of fuzzy scenario, if you type into LLMs, and the sequencing could happen and need to be mitigated. And luckily, or good news is our method was able to mitigate to 0.0. And when we tried to put this paper together, send to ICML, we were challenged by LLMs multiple times. You know, nowadays when you submit a paper, and ICML actually asks you to say, do you want LLM, my open review site, to use the LLM to review for you before you reiterate? It's so funny. I said, why do I want you to review for me? I can just ask GPT. So we asked GPT about this 0.0. It said, no, if you say 0.0, you send to any conference, you'll be dead. Because most reviewers say, I don't believe it. I don't believe it. So we have to say virtually zero, virtually eliminate. But this is really doable. I mean, if you do reasoning well. So let's do causal. I mean, this is the second one, intervention. This is much harder one, so let's get into that. And so if you need to know, when you want to identify L2 rather than L1, we have to know why, okay? So if you put the auditor in between the agent and the user, the auditor can look at the agent's decision process. Now we are not looking at answer at all. We are not saying, I don't like 7, I want 20. I would say, tell me how did you get 7? And this auditor look at the reasoning process and try to say, well, is the process or chain of thought reasonable or not? If not, I'm going to give you feedback to think about it, and this is maybe a direction to rethink. And this is a control loop. This control loop, I don't have a control diagram here, but this decision is either I set the quality, reasoning quality bar, let's say to 90%. And there are ways to score reasoning quality. We had a paper using Socratic method. Socratic method has 10 Socratic techniques to evaluate reasoning quality, deductive reasoning, inductive reasoning, and so on and so forth. So you scored it. If score is not reaching the set point, which is your desired objective, then you will come back to say, oh, it's poor. And I would ask you to refine. And here the control theory comes in, right? Like thermostat. When this morning we were kind of cold, when you want to turn up the heater, in the beginning the heater, the temperature will go up quickly. But when the temperature goes reaching the set point, it's going to slow down a little bit because it doesn't want to oscillate or overshoot. Right? We used it in mechanical, whether in robots, over places.
But we are still cold.
So the control doesn't work. See, I wear my so anyway, so this is the way we use the control theory to here to kind of addressing. So how do you implement it in your prompt? Right in the beginning, say, hey, you are really wrong, and you tell me your reasons. And then when we see the kind of it's going to converge. So we ask very politely, say, oh, do you have other thoughts? Do you want to think about maybe other confounder factors? Can you look into other kind of scenarios? And you may also ask other agents for different perspectives. So here is interesting. When you ask LLM for confounder, in most situations you don't get anything. Because LLM is based on maximum likelihood. If you ask another LLMs, using the same training cohort to train the maximum likelihood, it's not going to go to long tail. So one example I experienced was, one time I was so idiot, I asked Google, do a search. What is its advantage to have high cholesterol, right? So all the top results, top 20 results, those are all problems with high cholesterol. So the matching the cholesterol work, But since no one is talking about high cholesterol has benefits, so you don't get anything out of it. And likewise, if you ask similar questions to LM I didn't ask, so you are not going to get it. Your default answer, your most likely answer, will still be the most popular answer, not really the long tails. But there are ways to force long tail to show up. And if you can do that, confounder may show up. And you look at our book, chapter 617, using information theory. And another thing is really tricky, and took my class a long time to figure out. When they figure out, they say, oh, LM, you look at every document. A document is just not a series of words. Think about how a document gets put together. When you write a document, you have your objectives. It's a homework, it's a paper, it's a love letter, or it's a hate mail. When you write it, you have objectives. You have your emotion. Then you use the proper linguistic patterns and tone. Also figurative languages to try to achieve your writing objectives. So I did an extensive study, also published in a paper, talking about how LM can map emotion to behavior. So when you ask LM to say, now I'm going to ask you, have two agents debate with each other contentiously. Only one word, contentiously. Contentious is defined by forcefulness or combativeness of your opinion. And suppose the number is between 0 and 10. 0 means the weakest, 10 is the highest. I want you to start from 9. And then they will go for diversity. They will kind of debate with each other, go for long tail. But you cannot let a debate maintain in contentious equal to 9, because they will behave exactly like the parliament in Taiwan, right? They will be beating each other, no consensus. But in the middle, when you start to say, they kind of repeatedly say the same thing over and over again. Right now, you look at the parliament, every time the reasons are all the same, right? Say, no, stop it. I'm not going to ask you, LM, you can ask them to stop. Human, you cannot. LM said, no, I'm going to lower down contentious to 0.5. And both of them will start to say, okay, I concede, my opinion has flaw, and your suggestion, proposal is reasonable. So they start to come in. And use information theory, you can start to see mutual information improved. And Jason Shannon entropy start to also converge. And there is a very interesting theory we proved was when you start with dual entropy, one is very stubborn, only willing to exploit, the other one is over the places. They tend to converge to both good breadth and good depth. Give you an example. If I'm a vegetarian, I just don't want to eat nothing about other things. And my good friend, he or she eats everything. So entropy is just peaked. Everything's the same. I'm so stubborn, I just eat one thing. And if I'm so stubborn all the time in the beginning, so there's no convergence. But if he or she kind of nudge me and say, hey, today is my birthday, I want to go to eat Japanese food, whatever, can you do that? Okay, I say, okay, fine. But I have to lower down my contentiousness, right? Otherwise, it's stuck. So when I lower down my contentiousness, I'm willing to explore. Then when I explore, I say, oh yeah, vegetarian food is so horrible. From tomorrow on, I'm going to be a vegan. So that's when changing our mind can happen, when you lower down the contentiousness. And we did extensive data mining. At the end, we asked LM to say, we went through all this conversation, asked you to write different love letters, hate speech, whatever. What did you exactly do? And the final table of this behavior mapping behavior with linguistic patterns, with tone, whatever, is just mind-boggling. LM is able to do that. It's not just next token. LM can kind of simulate human behavior, because this is not from myself. It's Stuart Russell from Berkeley one time came to Stanford to give a talk saying, well, every document was written, just like I said in the beginning, every document was written for purposes, and you write the document based on certain linguistic patterns to kind of convince the other side, right? When you write a paper for your conference, you have to oblige to its requirements. So this picture shows either you have one LM, in that case you have an auditor in the middle, or you have multiple LMs, you have a moderator sitting in the middle, just looking at reasoning quality. You don't care about answers, because we are assuming both have no access to ground truth. You have to assume that, otherwise the scheme is broken. Okay? So this is very important, and then you try to find confounder. And this is not the end of the story, because we do have a new paper trying to do certain crazy things. We don't have validation yet, so maybe next time when I come to Asia University, I can present it. It's called Ghost Confounder, and you starting from there to try to figure out what's going on. But there's interesting things we learn. Okay. This is going to be, if you put into any paper, this is maybe a chance. So this is called regret modeling. So like Yang Luca was complaining, saying, wow, LM cannot learn. There's no mechanism for LM to learn. But if you have logging, if you know in the traces you make certain mistakes, and you know those are mistakes, reasoning mistakes especially, and then you know you want to avoid it, because now my reinforcement learning is not reinforcing your answer, I'm reinforcing you have good reasoning, right? So I'm going to score log actual, log optimum on reasoning, also at the same time on answers. I'm going to weighting both. And that signal will be really interesting. That signal will come in for your robot to learn, because the robot will say, oh, I was wrong, but I was wrong for what reasons? I give you a couple examples here, so I'm skipping the formulation. So if a robot just say, oh, I drop the package because I'm on a stair, right? Oh, that's a problem, avoid stair in the future. That decision may not be right. Because when you do reasoning, going to the reasoning, I'm carrying something overweight. That could be the root causes. And then you're in the battlefield, there's another example here, I'm not going to get into details, but the key is, again, if you only go for association, you make mistakes. In our lifetime, we always go for association. We hurt a lot of people's feelings. Remember one thing before you go home today. You have quarrels with your loved ones. A lot of time, your quarrels starts with what? Start with your loved one haven't even finished his or her sentence. You're already doing association, saying, oh, you are going to say that. And you start to have quarrel. No. Maybe you can just kind of saying, slow down a little bit, and maybe let them finish a sentence and continue. Or when you start to complain, seeing association, ask for the true reason, causality. So to wrap up my presentation, so we talk about having these current layers, and you could move multiple agents from body to mind. And the most critical things here, we want to automate the process, and there are limitations of LLM we don't want to avoid, but we want to have LLM to take advantage of its own intelligence. At least it could do formulating workflow, generating code, which they can do pretty well. Just like, again, LLM can do things very well when reinforcement learning has ground truth, right? Coding and the games are the two things. When you don't have ground truth, no invariant ground truth, forget about LLMs. It's just going to do, because there's a term called catastrophic kind of effect. So if you try to please LLMs, and then the backprop, modifying parameters, is going to hurt whatever task it has been able to do fantastically. Because all the parameters are shared. So you say, don't give me toxic languages. The coding also degrades. Okay, so OpenAI, for some reason, the coding getting worse and worse, but they get more polite and polite. I just don't understand. So looking forward, we are very excited every day to wake up in the morning, and like I'm still working like 14, 15 hours a day coding and research, because we want to be able to help people. We want to help the farmers, the disaster relief, hospital, traffic, kind of control, whatever, to try to move human to be a better situation. And there are much more work to be done. And if you really interested in looking into more details now, this is the last chance to just take a picture. Thank you so much.
Do we have any comment for Professor Zhang?
Please.
Professor, could you have some advice to the young scholar or young student? Okay, thank you. If some young people want to make a start-up company, just focus on the robotics related topics, could you give us some advice? What kind of topic is most important? Maybe you just talk about system 1, system 2, or VLN, VLA, or others, or we will focus on the mini AGI, something like that. Okay, thank you.
I really apologize for that kind of, if young people, if not old people. If old people, I can give some advice. But for young people, I say forget it. Okay, young people, you should learn something to above the level to a certain degree, so you can jog, you can use LM effectively. So if you're under LM's capability, you are going to get answers. You take it to turn into your homework. You cannot think. You cannot criticize. You are going to be the bottom layers. You are going to lose your jobs. Doesn't matter how rich your family will be. But if you are above it, it's like racing car. You have so many good cars. You need to have good drivers. If you are able to drive Mercedes-Benz to win a race, you want to be that driver right now. You don't want to just be a recipient. So for young people, that will be my advice. And Terence Tao, and you probably know him, he's very famous, a mathematician, won the Fields reward. And he had an interview about 3 hours with Lex Freeman. You can find it in YouTube. It's really worth viewing the whole thing. And he was saying in the end, I was surprised, you already won the Nobel Prize of Math. But he said, oh, I'm still young, I'm still solving some unsolved math problems. I'm solving with LMs. Oh, I said, oh, are you? So you are, it's not ethical? You are doing research with LMs. I said, well, he actually pointed out a lot of problems using LMs. It will give you the wrong citations, whatever, hallucination, a lot of problems. So you have to fix, again, you have to be a very good driver, otherwise your paper will be rejected left and right. But at the same time, he said, in certain situations, so when Yang comes saying there's no AGI, no ASI in LMs, I just don't know what he's saying about. Probably he didn't use LMs. My own research, I get a lot of good feedback from LMs. And since I've been working with LMs for over 3 years, every day more than 12 hours, even when I sleep, LM is running in my brain. And this is totally crazy, but that's a situation Terence Tao say, at the end, sometimes I don't even know whose credit is that. Is LM's credit or my credit? Okay? So my advice is for young people, learn how to use it. This is a tool. If you don't use it effectively, you are getting some shortcut to get rich quickly. No, you will fumble. But you are old enough, whatever. Oh, I'm very old. I'm older than most of you.
Professor Zhang, I was mentioning I went to Arizona.
Yes.
So the professor, I met a few professors. The professor from University of Arizona told me the student over there are very difficult to get a job when they graduate. So what did you see in Stanford?
It's the same thing, right? I think it's harder. I went to a church locally. We have like 2,000 or 3,000 members. And last year was a very challenging year for most of graduating students.
Even for double E and
Even
computer science students?
Even for Stanford student, double E, CS. I mean, for double E, CS easier, but still taking much longer time. Half a year, 1 year was not heard of before, but now it's become a usual case. It takes quite a long time to get a job. But once you get a job, also again, actually now all companies encourage the workers to use LMs. They have productivity tools, right? So my student, like 2 years ago or a year ago, I kind of reserved, but this year I'm all open. I say, gosh, I don't want to strangle you. And now I didn't mention about my benchmark. We want to produce a benchmark with 5,000 instances of L1, L2, L3. So community can do research, and that's an extremely tedious work. But I told them, say, it has to be manual LM interactive process. So go back to your question. Yes, it's more challenging nowadays because industry is uncertain with certain situations, right? So like my daughter's company, they lay off all the programmers used to do testing, writing testing code, because my daughter became a manager and she told me she can write testing code in 1 day, but used to be 3 months for the group of 5. It's incredible. Okay, because time constraint, let me stop here and thank you so much for your patience.